Hi, today I'm going to discuss the solution for Atcoder Beginner Contest 435 problems A to E. For problem A, we have a positive integer n, and we want to output the sum of all integers from 1 to n. And since n is really small, we can directly compute the answer. And now let's look at the code. So here's my code for problem A. I just inputted the value of n, and then I created this variable sum. Then I looped through the values from 1 to n and added each number to sum. In the end, I outputted the value sum. For problem B, we have a sequence of positive integers a of length n, and we want to find the number of pairs of integers L and R that satisfy the condition that the sum of all a from AL to AR, and for every integer AI is not divisible by this sum. So here, for example, in the case where A is 8, 6, 10, 5, 7, if L and R is 1 and 2, then A1 plus A2 is 14, and neither A1, which is 8, or A2, which is 6, is the divisor of 14. So in this case, 1, 2 would be a valid range, and we want to find all of the valid pairs of integers. And because n is small, it's only 50, we can directly compute by looping through all possible values of L and all possible values of R. To quickly compute the sum from AL to AR, we can use prefix sum. Then, after we've determined the values of L and R by looping through L and R, then we can then loop through all the values in between L and R and directly check whether it's a divisor of the sum. And now let's look at the code. Here's my code for problem B. This is the prefix sum, and this is the array that stores the values of A. So I first inputted n and A, then I constructed my prefix sum. Then I looped through all possible values of L and R, represented as I and J in my case. Then S represents the sum of AI in the range from I to J. Then first I said that this pair of integers is possible. Then I loop through all the values. If the sum is divisible by some value AK, then this means that this pair of integers is not possible, and I would break out of the loop and change the variable to false. That way, if possible is still true, then this means that this pair is possible, and I would increment the answer. In the end, I would output the answer. Next, let's look at problem C. For this problem, there are n dominoes standing in a row on a number line, and each domino standing at coordinate I has a height of AI. So we want to determine the number of dominoes that will fall if the first domino falls. And when the ith domino falls, all the dominoes in the range between coordinates I and I plus AI minus 1 inclusive will also fall. And this is because they will be hit by the previous dominoes. So how we can do this problem is at each position, we can keep track of a current effective height. And by this, I mean that maybe at a position I, the effective height is still 2, then that means that it would still hit values in 2 coordinates after it. So we can look at an example to make this more clear. So at the beginning, the effective height would be 3 because the first domino would be hit, and then this would create a height of 3 that would bump into the dominoes that go after it. And afterwards, now after we move on to, when we loop through the dominoes, when we move on to the second one, then we subtract 1 because we've moved 1 coordinate. And so now we subtract 1 by 3, which is 2. And the new height is 1, so it is less than 2, so we won't update our current height. So now when we move on to the next coordinate, now this domino has a height of 4, and the previous domino has a height of only 1. And because this has a height of 4, we will update the 1 to become 4. So now the effective height will become 4. And again, when we move on to the next one, we would minus 1. So how we would keep track of the height is we could record, we could use this variable to keep track of the current height, and then when we move on to the next domino, we would subtract 1 to the previous height. Then we would compare that value with the current domino to see which one is higher. Then we would change the higher one to the current height. So now we can look at another example. So the next one, so the previous one, this one would be 4 because the height is always greater than 0. Then that means that the dominoes will still topple over from the previous dominoes. So for this one, we have an answer of 4. And so now let's look at the next example. So here at the beginning, we have a height of 3. Then again, when we subtract 1, we have a height of 2. Then we will subtract 1 again, getting a height of 1, but then the maximum here because of the new domino is 2, so we will have 2. Then we will subtract 1 here, then we will get 1, so the maximum height is 1. Afterwards, we will subtract 1, and we get 0. So we know that we need to stop updating here because the height is already 0 when we reach this domino. So the previous dominoes are all not high enough to reach this current domino at the end. So that way we will just stop updating here and we will output the answer. So anytime when we're updating, if the previous height becomes 0 when we move on to this domino, we would just make the answer, we would just output the answer and stop looping through the dominoes because it would be impossible to for the dominoes to continue falling down. And so here the answer will also be 4. So this doesn't matter if this domino height is greater than this value because we already need to stop updating because this domino at the end will never fall down because the previous dominoes are not high enough to reach this current domino. And so now we can look at the code. So this is my code. I used the variable cur to keep track of the current height. And for each time, I just subtract cur by 1 because the height decreases by 1 when the coordinate increases by 1. And again, this is if curl is equal to 0, then this means that this current domino that we're on is not reachable by any previous dominoes. So we can just output the answer C out I and stop looping through the dominoes. But then if the height is still greater than 1, then we can find the maximum height between the previous dominoes and this current domino. So we can find max between cur and AI, and that way we can keep track of the current height. And in the end, if we haven't stopped the program, then that means that all of the n dominoes can be reached by the first one, and I just output n. For problem D, we have a directed graph with n vertices and m edges. The vertices are numbered from 1 to n, and the ith edge is a directed edge from vertex xi to vertex yi. And initially, all of the vertices are colored white. Now we have q queries. Each one has two types. The first type is type 1v, where color vertex v black. Then the second type, we determine whether it's possible to reach a black vertex following some edges from vertex v. So we can look at the first example. So first, we have this graph. It's a directed graph that forms these edges. So if initially the vertex 3 is colored black, and then we want to find whether vertex 1 can reach some vertex that is colored black. So we follow the graph starting from 1, it reaches 2, and then it goes to 3. And we know that 3 is colored black. So we can output the answer yes. So because we need to quickly output the answer for each of the type 2 queries, we can define an array called color I that represents whether the ith node can reach a black colored node. So we will store, for example, in this case, we will store an array of length 5 that represents each of these nodes. So whether these nodes can reach a black colored vertex by following the edges. Then for each update of type 1 query, we update all the possible nodes that can be reached by this current vertex. So for example, when we in the sample input, we first update this node and color it black. So in this case, we would update all the nodes that can reach vertex 3. So we will update node 2 and node 1 because they can all follow some paths to reach vertex 3. So now we need to find how to quickly update all the vertices that can reach the current vertex when we color the vertex black in a type 1 query. So how we can do this is that we can reverse all the edges on the graph. So these edges will become all reversed in this direction because that way it will allow us to update the nodes recursively. So for example, if the edges are reversed, we will get this graph. Then when we update the nodes, we can update the values recursively. So for example, when we color vertex 5 black, we can then update the value of vertex 2 and 4 because they are reachable by vertex 5. And after we update vertex 2 and 4, we can then update the nodes that 2 and 4 are connected to. So which is 1, yeah, 1 here. So for each time, we can just recursively update until the vertex that we're currently updating is already colored black. Then that means that it is already updated previously, then there's no need to update this time. And so this ensures that every node is only updated at most once, so it will not take too long. And now let's look at the code. So here is my code. This is my function to update the color. So I first have an array that's called color, and this stores whether the ith node can reach a black colored node following the edges that's connected to. So here is my graph that I reversed the edges. First, I input all the values of the nodes that are connected, and I put these nodes into a graph, connecting the vertex V to the vertex U. Afterwards, I input the queries. So in a type 1 query, if color V is already true, where true represents that it can reach a black colored vertex, then I would just continue because there's no need to update if it can already reach a black vertex, then that means that it has already been updated previously. And otherwise, we would start recursively updating the nodes based on the graph. So first, we will call update color, which will update the current node. So in the first case, I would always check that if the color is already equal to true, then we would just stop because this means that it has already been updated. Otherwise, we will update color V to true, which means that it can reach a black vertex, and because we've already reversed the edges, then that means that all the edges that follow this graph can reach this vertex. So because if we update the vertex V, then all the previous nodes that can reach this vertex is connected to a black node. So we can, because we reverse the edges, we can like loop back through the graph and update all these vertices to true for this color array to represent that they can reach a black vertex. And so we loop through the graph, and for each node that we get to, if the color is already black, then we wouldn't continue to update because it has already been updated previously, and otherwise we would just continue to recursively update all the vertices that this current vertex V is connected to. And that way we will update the vertices whenever we have a type 1 query, and when we have a type 2 query, we can just directly output the answer according to the value stored in the array. For problem E, there are n cells arranged in a row from left to right. The ith cell from the left is called cell I, and initially all of the cells are painted white. We have Q queries that we need to process, and for each query, we paint all the cells from Li to Ri black. And after we paint these cells, we want to output how many cells that are still painted white. So here, if the cells are painted white, they now are painted black, and cells that were painted black still remain black. And here, for example, we have 10 cells in total, and initially we paint cells from the range 3 to 5, and that means that cells 3, 4, 5, which is 3 cells, are all colored black. So we will output 7 because 7 remaining cells are still white. So we can solve this problem by storing ranges in a set. So because the value for n is large because it can be up to 10 to the power of 9. So that means that we cannot store n in an array. And instead, we can only store values of L and R. So because of this, we can store L and R in a set of pairs. And this will represent the values of L and R, where we can continuously store ranges that are colored black. So we can insert ranges that are already colored black. So for example, in this case, if we have these 4 ranges, which are some L, some R values, and then these 4 intervals represent cells that are already colored black. So now if we have this new range that needs to be painted black, so this range from Li to Ri is the new range that will be painted black. So we want to merge this with previous ranges here. And this is why we use a set, because in sets we can easily remove and insert new values with the time complexity very small. So here we will want to remove all of these ranges, and we will merge this new range with the previous ranges. So how we can do this is we can use upper bound to find the values of these ranges. So we can use upper bound to locate this range and this range. Then by this, I mean we can do like upper bound -1, or like here we can use upper bound to find Li. So here there may be another range, so we can use upper bound to find this value, then we can subtract 1 to find this value. And I will discuss this in the code later on. So, but we can just use upper bound or lower bound to locate these values, these ranges here. And afterwards, we can loop through the ranges from here to here, and then we can erase all these intervals. When we erase these intervals, we also need to make sure that we're updating the value that keeps track of how many black cells there are. So what we will do is we will also store a variable called black. And this keeps track of the current number of black cells. So when we remove these, we would minus this range, minus this range, minus this range, and when we add this new whole merged interval back in, we would add this whole interval back. So we would create, when we want to add this back, because this is overlapping, this would be new R. And because this is not overlapping and this part is smaller, then this value would be new L. Then we would add this interval called new L new R back into this set. So we would insert it back into the set after we've removed all these intervals because they are already covered by this one, and we would merge all of these intervals together. So what we would do is when we erase these intervals, we would subtract these values here, so the number of cells in these ranges, and then we would add back this whole new merged cell into this variable black. So this way we can keep track of all the current number of black cells that we have. So we may have another case. So there's actually other cases. This is one of the examples where Li and Ri are like in between the original ranges. Here it's one is like not in any of the intervals, but then Ri is in one of the previous intervals. So these still represent the previous intervals that we have already stored in the set. And again, we can use binary search like lower bound, upper bound functions in the set to locate these two intervals. So here. And what we will do again is we will find the minimum. So this part would be new L, and this part would be new R. And we will loop through these intervals that are overlapping or covered by our new interval from Li to Ri. So these are overlapping, so we would remove this, and these are covered, so we would also remove this and the last one. And then we will add back a new interval called new L and new R. We would insert this back into the set. And when we do this, we also continue to subtract these values from the variable, and then we add back this whole merged cell. So how we can solve this problem, to recap what I just said, is to remove overlapping intervals. We would remove overlapping intervals and we would insert the new interval that is merged. And we would keep track of the counts while removing. So subtracting these values here and adding this whole new merged value back into the variable black. So now let's look at the code. Here is my code, and one thing I did was that I initially set the value of black to 2, and then I inserted into my my set called intervals. My set called intervals represents the pairs of integers that are intervals colored black. So I inserted the value 0, 0, and n plus 1, n plus 1. These are not in the ranges of L and R, but I just inserted one at the smallest value and one at the biggest value. So that way it's easier to do upper bound, lower bound without worrying about the boundary cases. And it's fine if I just add 2 because when I output the answer, I can just subtract 2. But then this makes the code much easier because there's no boundary cases to check for. So here I input the values L and I. So now we want to find the intervals that is overlapping with these values. So I use upper bound to find upper bound of L to find the smallest interval on the left that's overlapping with Li. So we subtract 1 because there may be an interval that's overlapping. And then this is A is currently the smallest interval that's entirely covered by Li to Ri. So when we subtract 1, we can check if a second, this is the Ri of the previous interval, the current interval that we're on. So if it's smaller than Li, then this means that Li is like in between two intervals, so we can add 1 back to A. So basically this part is just finding the interval that's either like entirely to the right of Li or is in the middle where it's like overlapping with Li. And now we find this interval on the right side called B. With the same method, we do upper bound and we can find the interval that's like overlapping with Ri. And as I previously said, we would merge these intervals, so we would find the minimum value of Li and A dot first. A dot first is like the left boundary of a previous interval that's already like in the set. And we will find the maximum value to get the new R. And this is the sum, which is the value that we need to minus. So here, when we loop through the interval, this this while loop loops through the intervals from A to B, and it adds the ranges to the sum so I can keep track of the cells that are colored black. And then it erases the intervals. So this is the part that I mentioned previously about how we need to continuously keep track of the number of cells. So I just add all the previous values into this variable called sum, and then in the end I can subtract sum and add this new merged value to black. So here I'm just looping through all the like intervals from A to B, and I add them all to sum and then I erase them. Afterwards, I insert this new interval that we computed here, new L, new R. Then I output the answer, which is here, black minus 2 is the number of actual black cells. I do black minus 2 because we initially like created 2 additional black cells that we need to subtract when we output the answer. And we do n minus black minus 2 because we want the number of white cells. So we do the total number of cells minus the number of black cells to get the number of white cells. And this would be the answer. Thank you for listening to today's explanation.